Hey students, today we're going to be learning about seasons and the reason why we have seasons. To start off, you should go ahead and make sure you have the reason for seasons note sheet open. If you haven't already opened that, please do that. And then you should also open this interactive tutorial that goes along with the note sheet. So this is what we're going to be using in order to have a better understanding of how the seasons work. The first thing you should do for the reason for seasons note sheet is notice that there are some pre-assessment questions, A through E. And if you haven't already answered those, please pause this video and take a couple of minutes to just start thinking about the things we're going to be talking about by answering those questions. So stop and do the pre-assessment questions if you haven't done that, and then come back to the video. Okay, we're going to be talking about using this simulation here, this interactive tutorial to help understand what's going on. So let me orient you and let you know a couple of things. First of all, over here we see the Earth that is moving around, and actually it could be any planet. We've got Earth, Venus, and Uranus already set up here. And so you see there are two things that are happening with the Earth. First, the planet is spinning on its axis. And we call that rotation. So spinning on its axis is rotation. And as you guys know, the Earth rotates on a 24-hour cycle. And so that's of course, a day and night, right? Full day is a 24-hour rotation of the Earth on its axis. And if you're not sure what I'm talking about with axis, that's basically if you stuck a rod through the central location where the Earth is spinning on, that would be the axis of the Earth. The other thing that we see happening with the planet here is that it's moving around or orbiting the sun, which of course is not to scale in this picture because the sun is much larger than the Earth. But it gives us the idea of what's going on here. So we see that the Earth is traveling in its orbital path around the sun. Now, going all the way around the sun is called revolution. And for Earth, that's a 365-day cycle. So in 365 and a quarter days, and actually in that extra quarter is why we have our leap years, that's what the time it takes for the Earth to go all the way around, bloop, back to where it was. Okay, that's what we call, of course, a year. And again, that's revolution, the revolution of a planet around the sun. The other thing you see on here on our planet is a little X, and it's important. That location of the X is really important. It's showing us it's in the northern hemisphere, maybe at about 40 or 50 degrees in latitude. And that's really significant because of different latitudes definitely impact how the seasonal changes work. Okay, so we see that orbiting around there, and then here's a few other things we see. The angle of the sunlight as it's shining on the Earth or any planet is shown here. And so we'll see that change. We want to pay attention to that here. What this tells us is the more direct the angle of the sunlight is, the more solar insolation it's called. So this would be direct. The more direct sunlight that an area gets, or at a more of a 90-degree angle, the more light falls on a particular area. Like if we just take a square mile and measure how much solar energy falls, you're going to get a lot more solar energy that falls when it's closer to a 90-degree angle, or what we would call a more direct angle, than if it was a shallower angle like this. And so this is a main reason why our seasons are different, is because changes in the angle of the sunlight. So we'll talk more about that as we investigate this. Another thing that we see down here is the path of the sun down here. This is really telling us how long are the days. And we'll see that the days are longer for us in the summertime in the northern hemisphere and shorter, of course, in the wintertime, which, living in Colorado, you guys are fully aware that the days are longer in the summer and shorter in the winter. But we'll understand why that happens here. And of course, length of day is another really big reason why we have different seasons. And the longer the day, the more sunlight we get, the warmer it's going to be. And the shorter the day, the less sunlight we get, and it's going to be colder. So we can see that sun path. We can also trace the sun's path. You can see it's kind of leaving some dots behind, and so if we go faster, we can see that change happening. And then we've got another feature over here, which is the temperature. And this is mild temperatures would be like not real hot, not real cold, kind of what we experience here in the fall and the spring, fairly nice, pleasant temperatures. Warm and then hot would be up in the hundreds. Cold would be consistently down below 0 degrees, and so we'll like Celsius 0 degree, like below freezing. So we'll be looking at this as our seasons change. And there's just a couple of features down here in the controls. We can control how fast or slow the planet moves. We can also drag it up here, as I did. We can change the angle of the tilt of the planet here. And we also have some presets. So we have a preset for Venus, which is about 2 degrees off of its axis. Earth is about 23.5 degrees, and Uranus is about 86 degrees, completely tilted on its side there. And so we're gonna set this to Earth and just focus on what we notice happening. So let's go ahead and start in the summertime. So I'm gonna move the Earth here over to the summer. Now, down here it's telling me this is the summer solstice. The summer solstice is the day that's the longest day of the whole year. And so if you ever hear someone say the summer solstice, that's the longest day. And it's on a specific day each year, and that doesn't change very much. But let's look at a few things. So first of all, remember we're up here in the northern hemisphere. When our axis is tilted towards the sun right here, we have a more direct angle of sunlight. Okay, I'm going to move the planet just a little bit so you can see how that changes as we go through our revolution around the sun. But in the summertime, here on the summer solstice, we get the most direct sunlight. And it is still a little bit angled because we're in the northern hemisphere and the Earth curves away from the sun. And so there is still a little bit of an angle. But per square mile or kilometer, however you want to look at it, we get more direct sunlight, which means the Earth gets more solar energy per square mile in the summertime. That's because it's a very direct angle. And the other thing we'll notice as we play this here is the length of day. So look at our sun is pretty high in the sky. It comes up at about 5 in the morning and sets at 7-ish at night. And again, you guys know, living in Colorado, that we have pretty long days in the summer. So think about those two factors. We have very direct sunlight. There's more sunlight falling per square mile in the summertime, and the days are much longer. So overall, in the summertime, there's a lot more sunlight that's happening, that's falling on the Earth in the northern hemisphere. And that's primarily because the axis of the Earth is tilted towards the sun, which gives us those longer days and a more direct angle. Also, if you notice our temperature over here in the summertime, we're above mild, so we're getting into the warm temperature range. We're not hot, we're not blazing hot, but we are getting towards the warm here in the summertime. Let's go ahead and move forward a little bit here. So we're going to move on to autumn or fall, so this direction, and we're going to see here the equinox come up. So here's the autumnal equinox, or the fall equinox. And if you know your Latin and Greek terms, equi is equal and nox stands for night. So the autumn equinox means equal night. It's the same time that the sun is up during the day as it is down for the nighttime. So that's why it's called the equinox. And over here we'll see that there's the spring equinox, which we'll get to in a minute. So in the autumn equinox, I want you to look at how the tilt is. Now notice, as we went from here to here, the Earth is still pointed at the same direction. So it's pointed up in this direction somewhere, the tilt of the Earth. Some people think that the tilt of the Earth actually changes, and that's not accurate. The tilt of the Earth is always pointing in the same direction. What's changing is our location relative to the sun as we revolve around the sun. Okay, so at this autumn equinox, so when it's fall time, our Earth is not tilted directly towards, and it's not really tilted directly away. It's kind of in between. And so what we see is the angle of light that's coming in is not as direct, but it is definitely a more shallow angle than it was in the summertime. That means that that light is spread out more over every square mile. So the amount of sunlight that falls on every square mile in the fall is less than it was in the summer. So we get less overall light that is hitting each area of the Earth. The other thing that we see in the fall is our length of day is a little shorter. So our sun is not as high in the sky. It comes up a little bit later in the day, and it goes down a little bit excuse me, earlier in the evening. So our length of day during the fall is a little bit shorter. So again, if we put those two things together, we have a shallower angle of sunlight, and we have shorter days in the fall. And look at our temperature; it's gone down to mild temperatures. And if if you lived in Colorado for very long, our falls are beautiful. We have great 60, 70 degree, nice cool days where you're not too hot and you're not too cold. And that's just a beautiful thing about living in Colorado, is our nice mild fall and springs that we have. Okay, now let's go ahead and keep going here. So as our planet moves, again, pay attention, the direction of the tilt doesn't change, all right? So as we move this way, look at what's changing. Now we're in the winter time. Okay, I'm going to put it on the winter solstice. So the winter solstice is like the opposite of the summer solstice. The summer solstice was the very longest day of the year. The winter solstice is the shortest day of the year, which is about right there. Okay. Now, in the winter time, we in the northern hemisphere, we are tilted away from the sun. So that causes our angle of sunlight to be very sharp, very steep angle, which means that that light is spread out over a much greater area than it was previously in the fall or the summer. That means that every square mile of Earth in our area during the winter time receives much less insolation or solar. Insulation is not the same thing as you put in your house to keep your house cool and warm. Insolation is referring to the amount of sunlight that hits the Earth in a certain area. So we receive less sunlight per area in the wintertime. And then of course look at our days. So here comes the sun at 8 or 9 in the morning, and it sets at 4 or 5 in the afternoon, and we get very short days. So those two things together, our short days and our very shallow angle of sunlight, causes us to have much cooler temperatures in the winter time. Okay, let's keep going. Just for a fun fact, it takes about 90 days between each of these seasonal changes, about 91. So if you take 365 and divide it by if you take 365 and divide it by 4, for the 4 different seasons, it's about 91-ish days. So to go from our summer solstice to our fall equinox is about 91 days. And then here's about 91 days. And just to make a quick point, this Earth, as it rotates on its axis, it is not rotating fast enough. If you think about it, it's only rotating about 7 or 8 times to go from here to here, and it should rotate about 91 times. But that would be going really fast for this model. So that's one thing that is a little flaw in here, but it still helps us understand a lot. Okay, let's move on to the springtime. Now, the spring equinox is on March 20th. And we're filming this video on about a month later. And so if I was looking at where are we right now in our orbit, our orbit around the sun, maybe we're about right here. So we're getting more towards the summer. We're fully into spring. But if we're going to the spring equinox, and remember that means that equal day and night, just like it did for the fall equinox. Now, again, our angle is it's a little bit more direct than it was back in the wintertime. So we're receiving more insolation or more sun per square mile on Earth. Our day length is kind of the same as it was back in the fall, okay, medium length days. And so overall, our temperatures are back to mild. Now, one thing to keep in mind, there are a whole lot of other factors going on here. There's high and low pressure systems, and there's the high altitude winds like the jet stream that affect our temperature, that affect our weather. And so, you know, you guys know in Colorado in the springtime, we get some crazy weather going on, massive snowstorms and then beautiful days. And so we get some weird stuff going on, and that's partly because of what we're talking about here, the overall seasonal changes. But there's a whole lot of other factors that are going on, just so you know. All right, so very similar situation here. Now, if you haven't been, you should kind of be drawing these into your learning about the season simulation, like in your sheet. And we've provided a couple of examples for you, so that just snapshots of these different like different times of the year. So if you haven't been drawing these in, maybe take a second, stop the video, and draw in your summer solstice. And you might need to bring this up and go back and review where that was, the path of the sun, so we know how long the day is. And really, you want to make sure when you're putting these in, you exaggerate. The angle of the sunlight is really important, and the length of the day. And if I was doing these notes, I would also just make a note off to the side when you draw the sun path on your worksheet. I would say long day, short day, medium day. Like, try to put some context around that, so you're not just looking at where the sun is, but you're making that connection. You might also just want to mention the temperatures. So in the summer, we have warmer temperatures, in the fall and the spring, mild temperatures, and in the winter, cooler temperatures, which you probably already know, but you could include that to help you out. But the angle of the sun and the length of the day are the most important things to be aware of. And then the tilt of the earth, of course, is what's actually causing that to happen. So as we go back to our summer here, we've gone a full year around the sun. We've done our full revolution around the sun, and that's taken us 365.25 days. And we go back to that more direct sunlight angle. We have longer days, and so we get a lot more warmer temperatures here. All right, let's take a look at what are some changes that we could make here. Let's just pretend that Earth had the same tilt as Venus, or actually we'll just put it at 0 degrees, no tilt. And I'm going to go fast forward so you see what happens. What if the Earth's tilt was 0, or it had no tilt on the axis? And watch what happens. There is no change in the sunlight angle at your location on Earth. There is no change in the length of the day. And so the temperatures really remain the same. So if there was no tilt on Earth, we would really not have any seasons. It would be about the same temperature and length of day every day of the year. And to me, I think that'd be kind of boring. So I'm glad that we have a little bit of variation. Now let's change the angle just a little bit, okay? And so I'm going to put this at like a 10-degree angle here. All right, let's see what that looks like. Remember, Earth's angle is about 23 degrees. So let's see this. All right, so we're getting some change. The angle of sunlight changes a bit. All right, but it's not as dramatic as it was when we had it set on Earth's axial tilt of 23 degrees. So we're not getting as much of a seasonal change. We are getting a little bit of seasonal change. And I can even exaggerate that a little bit if I put it to maybe like 6 degrees tilt. So really the key point here is the less of the tilt on the planet, the less that is tilted on its axis, the less of a seasonal change that we'll have, meaning there's not going to be as big of a difference in temperatures between winter and summer. And you might be wondering, do other planets have seasons? And the answer is yes. All planets have different seasons, but if you look at Venus, which only has a tilt of 2, its seasonal changes are very small. And of course, when we talk about seasons, we think about temperature and rain or snow, those kinds of things. And every planet's a little bit unique because every planet's atmosphere is much different than ours on Earth. And so it's not going to look the same, of course, on Venus, which is covered in sulfuric acid rain and bad things like that. But you can see there's very little variation in the daytime for Venus and the angle of sunlight throughout the year because it has a very small tilt. Now let's go over to Uranus. So Uranus is pretty unique in that it's tilted almost at a 90-degree angle, 86 degrees. So it's like somebody took this planet and kicked it on its side and it's orbiting this way. So look at our length of day and our sunlight angle. If you were in summertime, if you were in the northern hemisphere of Uranus, all right, look at your length of day here, all right. The sun would actually never set. But as we get to fall, we get more normal, and then when we get to the winter time, the sun would never rise because it's blocked by the shadow of the planet. And so you basically would have in the summertime very, very long days, all day long, sunlight all day, and very, very long nights in the wintertime. Now, if you've ever been to maybe Alaska or somewhere very far north, you've actually probably experienced those very long days in the summertime, or maybe you've been there in the wintertime and you've experienced those very long nights where you only have about 3 or 4 hours of daylight, and that's similar to what's experienced here. It's just not quite as much, and that brings up a good point that the location you are on Earth is definitely affected. Like your latitude definitely affects how you have seasons. If that X were more down here on the equator, because that equator is always directly facing the sun, we don't get very much seasonal change along that belt, along the equator. But the farther we get from the equator, the more seasonal change we get. And so we see that way up here on the poles, we get a much greater angle of sunlight because the Earth's curvature is more, and so they have much greater seasonal changes, like up in Alaska or up farther north. Another point would be that if you look at this planet as it's orbiting around, so this is back to Earth's tilt, okay? In the wintertime for the northern hemisphere, which is where we are, what's the season in the southern hemisphere below the equator? And that is actually tilted towards the sun. And even though it seems to be on the bottom here, there really is no up and down in terms of the universe. So if we wanted to say the southern hemisphere of the globe is pointing towards the sun when it's our wintertime. And so down in Australia, it's summertime when it's our wintertime. And if we were to go somewhere in our summertime, if we went to the south, somewhere south, it would be more of the winter season because the southern hemisphere is tilted away from the sun whenever it's our summertime. So I want to just go back to the worksheet here and make sure you understand a few things. I'm going to leave this simulation up and I'll leave it running, but I want to answer a few of the questions and just make sure you have those down. So one of the things it asks on A is, why does Earth have seasons? And it's really important that we use the planet's axial tilt. So how does the tilt of the axis affect the sun angle, the temperature, and the path of the sun? And so what you should mention in there is that there are certain times of the year when the northern hemisphere is point tilted, the axis is tilted towards the sun. That gives us more direct sunlight, which gives us longer days, and that's in our summertime. And there are times of year when the axis is tilted more away from the sun, and those are the times where we see the angle of sunlight is less, and so we get less sunlight and we have shorter days. So if the planet wasn't tilted, we wouldn't have those big changes. So it's really the tilt of the axis and its revolution around, like its path around the sun, that causes those different seasons. B says, consider what you observed with Uranus and explain how the sunlight angle, temperature, and path of the sun are different. Well, when the tilt is so different, when it's at maybe 90 degrees, it was 86 degrees, when it's so different, the angle of the sunlight is much different. It's in the wintertime, you get very, very little to no sunlight at all because of the extreme tilt. And in the summertime, you have sunlight all day long. So the length of the days are very long or very short or non-existent on whenever we have more of a tilt. And the amount of sunlight you get is very extreme. It's either direct all day, or in the wintertime you get no sunlight at all. The C is asking, would a planet with no tilt have seasons? And the answer, as we saw, is no. There really wouldn't be any seasonal changes if you were in the same spot. You would always experience the same length of day. And the reason why that is without that tilt, we get the same amount of sunlight all year round, no matter where we are in our path around the sun. And so that without that tilt, to have that variation in sun, our amount of sunlight and length of day is the same if there's no tilt. But we do have a tilt. It says during which season on D, which season is the angle of sunlight in the northern hemisphere the lowest, and how is this connected to the weather we experience? So the angle of sunlight is the lowest, or if you want to say the shallowest, it's not very direct, in the winter time. So if I move my planet here, I'll set it back to Earth, and I'll move it over here, and we get a very shallow angle of sunlight. And of course, that gives us very colder temperatures. And so in the northern hemisphere, we're going to experience snow instead of rain and colder temperatures. E is referencing if we travel to New Zealand, which is by Australia, if you're not sure with your geography, down in the southern hemisphere, and we wanted to go hiking and enjoy the beach, so you want it to be warm. What time of year should you go? Well, remember, if it's in the southern hemisphere, it's going to be the opposite season as the northern hemisphere. So if we want it to be warm, we need to go when it's cold here in the northern hemisphere. That would be in the wintertime, so we should probably plan our vacation to New Zealand sometime in maybe December, January, February, when it's going to be cold here. So we'll get away from the cold, get to the southern hemisphere where they're experiencing that summertime weather. And the last question, how does the latitude affect seasons, weather, and climate? Now, again, I already mentioned this, but if you're on the equator, the angle of sunlight really doesn't change a whole lot, and so you don't have as much seasonal change. There is some, but not as much seasonal change whenever you're at the equator. The farther you get from the equator, because of the curvature of the Earth, that creates a greater angle with the sunlight. And so the farther north or south we are from the equator, the more extreme seasonal changes we're going to have. So if you went somewhere like Florida, which is kind of in between us and the equator, well, not quite as closer to us, but you don't get as much of extreme changes in the Florida seasons because it's closer to the equator and it gets more direct sunlight. But you get farther to the north, like we are in Colorado, and the curvature of the Earth is a little bit more, and we always get a little bit less direct sunlight, and it's more exaggerated when we're tilted towards or away from the sun during the summer and the winter time. So I hope this helped explain the seasons, and there's a whole lot more to this, and there's a lot of misconceptions about seasons, but I hope this has cleared things up, and hopefully by now you can answer the question, why do we have seasons on Earth? Thanks for watching.